Hey, that looks like we are live. Hi, David.
Hey Alex, how's it going?
Yeah, great. A little bit interesting things happening today, but whatever, we are here with all the people, and that is amazing. I see multiple dozens of people join it already. So, hello, everyone. I see Artyom in the comments. Hi, Artyom. Connection is excellent. If you can see us, if you can hear us, then please let us know in the YouTube chat so we know we can start. But at my side, everything looks green actually. Stream is healthy. Hey, ciao Christian, come stai? We have people from all around the world, I guess. Well, we will see soon how it goes. So let's start. Well, today with you, developer advocate Alex Voloshev, that's me. My job, primary job in IT is an IT exorcist. There are some stupid mistakes and misconceptions people doing permanently in their jobs as software developers, operations teams, and I hate it. So my job to help people get rid of those demons, but not software running in background, but mistakes they're doing and use right tools in the right way exactly when they need them. Today with me, David Chang, developer advocate at DataStax. David, could you please introduce yourself?
Sure, and I see that it says developer question mark architect. That should be a forward slash. My background's developer architect. I've been in the industry for over 30 years, and I've taken a circuitous path to Apache Cassandra and DataStax. I've worked in desktop applications, embedded in real-time systems, machine controls, defense, finance, sort of you name it throughout the industry. But one thing that's been common in every place that I've worked, from mobile development to embedded development to enterprise development, is data. It's always all about the data. And even in this brave new world of AI and generative AI and machine learning, there is no AI without data. So
Right.
eventually I found my home in the data world and am just loving working with Apache Cassandra and helping people learn how to solve problems with Cassandra.
Yep. Cool. So yeah, you are totally right. And then let us keep moving. Today it's a workshop about NoSQL. And workshop part means what not only me and David are going to do some work, but you are going to do it too. We believe in hands-on learning. That means what you are not only listening, but you are working, you are solving tasks, you are pushing buttons. To organize that in the best and most convenient way for you, we use free primary platforms to make this workshop live and keep it in action. First, all the source code is open sourced and it's available on GitHub. Then for our data, we use AstroDB, which is basically managed Apache Cassandra, so Cassandra in the cloud. And I don't remember if for this workshop we are using Gitpod. David, we're actually using Astra CLI in the browser, right?
Right. You'll be able to work directly in the browser through our Astra user interface. And Alex, just to remind you, this is the one of the workshops that we've ported to Academy, and
Yeah.
all the updated content is on datastacks.academy.
Yes. Okay. So I hope this part is clear. Now, completing this short course, you are getting your participation certificate, or we call it just badge. So you can brag on LinkedIn or Facebook or whatever you prefer. Only thing you have to do is to watch this stream, preferably live. But even if you watch it recorded, you still can ask your questions using our Discord server. And then answer the quiz in the end of the Data Stacks Academy course. Link is attached. Good. So now I'm going to ask you some questions. And to answer my questions, you go to menti.com. Easiest way to do it is just to use your mobile phone. And you can scan this QR code, or you can go to menti.com manually and enter the code which is on the screen, 97038858. Questions will be coming all through the workshop again and again, different questions, of course. So don't quit, then the first set of questions will be done. Yes, and the link or the coach will be available using comment Menti. Yes, oh, right. Thank you, David. Right, it's everything is here already. And Nightbot is assisting us. So good. Let's move on then. Code to join will be on the screen, on top of the screen. So feel free to jump in later. So what's your experience with relational databases? A bit, a lot, black belt, okay. There is someone with left join group by black belt, totally. I see some people only beginning their path, or maybe already too tired of relational databases and not using them anymore, so forgot nearly everything. But most of you have some relational database experience, or a lot of that. That is totally great. We will discuss relational databases in a moment. Good. So let's keep the questions coming. What's your experience with NoSQL databases? Plenty, a little, known, little, plenty, okay. But you see, David, we have we have some NoSQL experts. That is good. If you have no experience, don't worry. That's introduction level workshop. And those people who have solid experience with one group of NoSQL databases, this experience will not help them with another group of databases. In general, one of the biggest demons I'm constantly fighting in my job as IT exorcist is this misunderstanding of what a NoSQL truly is. And those are totally different databases. Oh, you will see in a moment. No, meanwhile, let me ask you one more question. But this one, please answer in YouTube chat because it's not added to this deck, but I still want to know your answer. What do you think about statement, NoSQL is schemaless? Do you think NoSQL is schemaless, or do you think maybe that's not perfectly correct statement, or you know what is perfectly incorrect statement? I'm very curious. Not sure. Well, that's a good answer. Sure, why not? And meanwhile, last before we proceed,
Yeah, Alex,
and yep,
I think you asked a trick question.
yes, sure. That's a very tricky question. You know, I'm doing this job for quite a long time, and I love asking like pretty advanced questions. You see, we have people with pretty strong relational database experience and some NoSQL experience. So, oh, yeah, NoSQL has its own schema, not like, okay, it's not schemaless. It's not. I think it depends. It depends. Fit for purpose. Schemaless. So, people, one last question. Okay, while you are answering where are you located, I will ask one more question about NoSQL. How type any number you think. How many NoSQL databases in the world, or maybe yeah, how many NoSQL databases in the world currently exist? What you could go and use? Is it 5, 50, 500, or whatever? What do you think? No idea. Good answer, fair answer. Perfectly. Hi, Mohammed. 5 or 6, 150, 25, no idea. Anyone else? About 100. More than 10? No idea. 5. Few dozens. Under 10. One ring to rule them all. Yes. More than 15. Okay, so if we go to dbengines.com, you will see what currently known more than 250 NoSQL databases. And most of them belong to totally different families. Graph databases, columnar databases, key value databases, those are different databases for different purpose. So if your answer is NoSQL is schemaless, I'm sorry, but I just did my job well, and that is a wrong answer. NoSQL, some databases are schemaless, and some are perfectly structured, have tables, and that's perfectly fine. You will see in a moment.
So, Alex, I think that makes every possible response, some, none, all, other than all, correct.
Yes, yes, yes. But yeah, there are plenty correct answers. Yes, there are very many NoSQL databases, actually a couple of hundreds, and some of them are schemaless, and some of them are pretty schemaful. And graph databases are schemaful, for example, although they don't have tables as is. But let me keep moving. And meanwhile, we have people from all around the world. I see a lot of Africa, India, Europe, United States. No one from Australia. Those lazy guys must be sleeping. It's going to be like pretty late now, right? So let's move on. Yeah, and I believe answer at least one is perfectly correct. Yeah, definitely. Well, then last question. What database you are using the most currently, or maybe was using in your former project? Yes, that's pretty interesting to see people from some interesting places. Yeah, this one better to answer on Mentium, so we will see a nice visualization of what Word as a database that must be painful. I see Cosmos DB, Oracle, quite a lot of Oracle actually. That's interesting. Cool.
Yeah,
Postgres, of course, pretty much
it beats
expected.
you. Yeah.
Some people using Cassandra, and that's great. That will be introduction, but I still will try to surprise you. That usually happens. Okay, HBase. Haven't heard this name for quite some time. Aurora, okay. DynamoDB, well, pretty much expected. Cool. So I hope everyone who wanted to join it already. And that means we are going to next part. But before we go to the next part, we are going to talk a little bit. So relational databases were dominating databases market for literally dozens and dozens and dozens of years. And they are perfectly great. Some people now say what NoSQL databases will replace relational databases, and that's a complete bullshit. Like that's not totally not happening for many projects. Relational databases will be a perfect choice, well, nearly forever, I would say. Although not for all. You will see soon what I'm talking about. But biggest limitation of traditional relational databases was the biggest reason for people to start to develop something different, so NoSQL databases, is their very limited scalability. Amount of the data on the planet grows very quickly. And recently, there were very interesting research done by IDC agency, ordered by Seagate company. Maybe you know Seagate, they were pretty famous producers of hard disk drives some time ago. By the year 2010, overall amount of digital data on the world was estimated to be 2 zettabytes. Currently, by this year, it's estimated around 120, so basically 60 times bigger, and it keeps growing faster and faster. So, few requirements have changed. We will speak about requirements a lot in the first part of this workshop. More volume, we need more and more to store more and more data. We need this data to be dispatched faster and faster. Before, your internet service provider was lazy and slow. Most of the people had slow internet connection, so it doesn't matter if your database is fast. Now it matters a lot because everyone has fast internet connection, even on mobile phones. And then finally, we didn't want to store only strict schema data. One of the most famous early NoSQL databases was Mongo, and obviously, as it was considered schemaless, or better to say flexible schema, because schema technically present, it's just hidden from a developer. Then, yes, well, NoSQL became known as schemaless, but it's a mistake. NoSQL can be schemaful. Good. Yeah, and that is zettabytes, right. Cool. So, now, that is a really so common misconception. I spent years fighting it, and I actually kindly ask you to join me in this crusade. People thinking of NoSQL databases as document databases. MongoDB, DocDB, all this bunch of things, you are throwing JSON documents and you have them stored somewhere. That is cool. That's a great family for many projects. It's will be a perfect choice, but not for all of the projects. And you know, there are very different tools that still NoSQL databases. Graph databases. Graph databases are interesting. That the graph databases, you we call relational databases relational, but you know what? They are way less relational than graph databases. In relational databases, relations are actually second-class citizens. Then you create a relation between two entities when you make this kind of a foreign key linking to entities. Can you put the date and time when it happened? Could you put some properties on this relation? No. Then if you want to have something like that, you will need a new table, and then that's not a relation anymore, but just new entity, a new table in your database. From this point of view, graph databases are way more relational than relational databases per se. That sounds a little bit weird, but that's exactly how it works. In graph databases, you have much better control over relations, and they have real properties, and you can explore those graphs, and like relations are truly first-class citizens there. Is that it? No. We speak about key value databases like Dynamo or Redis. People mentioned them a lot today. There's also NoSQL. They don't support SQL. They are non-relational databases, and they are great databases. They're perfectly matching the definition of NoSQL, and they are strict schema. You have to declare schema in DynamoDB, for example. Object databases, special use case, still doesn't support SQL, still stores data. Tabular databases like Cassandra we will speak about today, but also Google Bigtable. Time series databases, maybe there are some people like me with operations and monitoring experience, site reliability engineering things like Prometheus, mostly probably you are using Prometheus already. And ledger databases, what also a very separate case, and that is still NoSQL database. Your experience with Mongo will not help you with Neo4j. Your experience with Neo4j will not help you with Cassandra. That's why literally any statement about NoSQL is or NoSQL was is wrong, because people are actually speaking about very different databases, very different families of databases, sometimes completely opposite kind of databases. So that's why I say be careful with this definition. NoSQL is way too wide. Okay, so we have a few hundreds of NoSQL databases. Today we are going to speak mostly about Apache Cassandra. Why Apache Cassandra? It's one of the most powerful databases on the world, and it's definitely the most powerful open source database. There are some proprietary solutions based on the same white paper, like Google Cloud Bigtable, for example, or DynamoDB, but those are proprietary. And I'm a personal and big fan of open source. So I'm an open source maintainer, contributor. I write a lot of open source code. All our education basically is open sourced. And that means but we prefer to work with open source with no vendor lock-in. Bigtable is great, but if your application is tightly closed, tightly coupled with Bigtable, and you decide to move from Google Cloud to Amazon Web Services, like good luck, people. You are going to rewrite half of your application, right? Cassandra is open source, so if you are not happy hosting it or running it on Google Cloud, you can perfectly move to your own data center or Amazon Web Services or whatever, or maybe think about Astra, we will mention later. But yeah, that's the idea. We love open source. Yes, Jose, slides are going to be available for sure, and like there are plenty of additional materials you will see soon. So, but why Cassandra? But why for now? I mean, not why you should use that. This question you will answer on your own very soon, should you or maybe should not at the moment, which is also a pretty valid answer. But first question I want to answer is why Cassandra was originally created. And last point before we go in, there is a discussion on how do we train our developers, how do we train engineers using Cassandra. Are we going to answer a question how to use or how it works internally? And some people say like no one cares how it works internally. People just want to know how to use that. And you know what? People what only want to know how to use that, I don't call them engineers. Those are people who press red button, then red light is blinking, or press green button, then green light is blinking. Those are not engineers, sorry. Engineers must understand how it works internally. So today we will do a deeper dive than people normally do on how Cassandra works internally. Only this way you will understand how to use that right and then better do it or not.
And the benefit, of
Yeah.
course, to that, Alex, is that knowing how it works internally, as opposed to, say, working with Oracle, allows you to really get the most performance out of it or the most consistency, really to tune it and fit it to the problem you're trying to solve. So it really is important that we understand both the high level of how to use it and the lower level of how it works.
Yes, of course. Yeah, that doesn't mean we are not going to tell you how to use it. No, we do, of course. But not only that, because only that will be not enough. You don't want your airplane pilot to be trained on only how to use it, because then everything is green, you will be fine. But then something goes wrong, you are going to have not a nice landing. So this disclaimer, don't try this at home, is actually, of course, a joke. Please try this at home. Please learn
Yeah.
things, follow things up on our Data Stacks Academy. We have training grounds where you can try everything in the cloud. You don't have to deploy anything on your own machine. Please try this at home, but there are still some things I recommend to avoid. First, have any one of you ever heard about Fang-driven development? Or maybe now we should call it manga-driven development. What was that? Meta, Apple, Netflix, Google, Amazon, right? Have you
Yeah.
any one of you heard about Fang-driven development or manga-driven development? No. Anyone? Nope, nope, nope. Okay. Okay. Oh, that means you are pretty happy people because I did heard and even saw this in action, and that's always hurts my architect's heart a ton. Fund-driven development is the development like approach to development of a software projects. Then companies are picking software solutions, picking databases, picking different tools, just because some huge company using this product. Like, yay, Netflix uses Cassandra. Let's go use Cassandra too. People, Netflix uses Cassandra for Netflix size problems. That doesn't mean Cassandra is a good or bad fit for you, but you need to analyze your scenario and think like when it fits, when it's not, and you better understand consequences, price to pay. I don't mean money, I mean limitations, because there is no silver bullet in a database world. So fund-driven development is then you develop your project based on some cool technologies what huge companies are using. It's nearly always lead to some huge problems. Now, next question. Have you ever heard about CV-driven development? I also saw that so many times it always makes me crazy angry. Nope. Anyone Anyone ever heard about CV development or maybe did? If you ever did, then please stop. Cool. You all are amazing people. Thank you so much. Because CV-driven development is one of the biggest, dirtiest sins in the what you can do to your employer. CV-driven development is then employees, software engineers are pulling some technologies in the projects because they want to put those into their CV, curriculum vitae, basically to put that into resume. You don't care what if it fits your project or not. You just want to use it and you pull it into your project. And now project is half broken and everything is slow, but your CV has some new shiny words. That is awful. I consider that basically as a crime, and we fight it very thoroughly here. So please don't do CV-driven development. And that's very important for us, like to really stop this. Let me give me a moment to restart. Yes, that should be good.
Someone noted
Oh,
that during Corona times, many folks did CV-driven learning courses, and I'd say it's not a bad thing.
yes.
Learning is always good.
Learning is always good. Learning is always good. CV driven development, when you put projects, when you put tools into your project based on what you need, not your company need, is not good at all.
Right.
Good. So I am happy we understand each other here. And finally, today we work with one of the most powerful databases in the moment, and that's extremely advanced, complex, and efficient technology. And great power comes with great responsibility. Great responsibility in our case, it means what you need to learn how to land before taking off. Otherwise, you are going to have crash landing, and we want you to avoid that. If you're getting to an airplane pilot cabin, you see 1,000 of different knobs and levers, and you better not take off without learning how to use all of those. Exactly the same happens with advanced distributed decentralized technologies. That's what we will be doing today. Help you to learn how it works. So, how it started. In the year 2008, Facebook reached their first 100 million users. That is a huge number. And they were, I believe, first publicly available company that reached, maybe there were some others, but I believe Facebook was number one. But situation this time, it was not only about amount of people. Situation was about some more uh, requirements, what weren't a big thing before. Users all around the world, all around all the continents. Doesn't matter how fast your database. If it's deployed in Europe, customers in Australia are not going to be happy. Next thing, fast internet connection. I mentioned that already. Beforehand, your internet service provider, last mile mostly probably, was the slowest piece of chain. Now, chain link. Now it wasn't anymore. Now more and more people had fast internet connection, even for mobile phones. Well, 2008, maybe not for mobile phones, but still for laptops. Yes, for sure. More and more data. Sadly, Facebook doesn't open how many data they have, but those quite some numbers. We speak about petabytes, maybe hundreds of petabytes. And of course, now very strict high availability requirements. So a lot of things changed. Before, all of those points weren't really a thing. Situation totally changed. So they had encountered some problems. What weren't a big thing before, and that led to a little bit of discovery. There is no database to answer those situation. Now we are going to become all of us. I see there are dozens of people on the stream. Perfect. Now all of us going to become software architects, and we are going to think like software architects. And architects, first thing they do, they define requirements. So that's what we are going to do. If you don't know where you're going, every road will get you nowhere. And our requirements going to look like that. In comparison with the previous things what databases were asked to do. First, now we have users all around the world, and that is a pretty strong requirement. It was new by that time. Then volume, we are speaking about millions of queries per second, millions of queries per second again, maybe dozens of or hundreds of queries per second. Then volume, so a lot of data, really a lot. We are going to have nearly immediate response. That's very important for us to have strict SLA on time. SLA means service level agreement, and that is something what we promise to our customers to deliver. SLA on response time means like we are going to answer most of the queries within, I don't know, 12 milliseconds, basically. I mean, you can define different restrictions, but that's what SLA on time response time means. But also, we have one more SLA, service level agreement, on high availability. High availability, so HA SLA, means how much time we are going to be available. Are we going to be available all the time, or we can afford some downtimes? People hate downtimes, so we need to stay uptime like nearly always.
And Alex, if I can
Yeah,
jump in here,
of
as you
course.
look, for those of you who are new to NoSQL or new to Cassandra, you're going to see some things here that look very foreign from your relational database experience. And you'll look
Yeah.
and say, why did Cassandra do that? And the answer is this slide: to meet users' needs all over the world at high volume and provide the high level SLAs for performance and for availability. And that's driven many of the design decisions that will seem completely foreign or out of left field from our relational background.
Yes, yes, perfect. Thank you so much, David. You are perfectly right, and that's very good you mentioned that. You see, I hear from time to time, like from developers who have no understanding on why. Like why, I believe, is the most important question in IT and software development, and people very often ignore this question, and that leads to many mistakes. I'm on a recent conference. I met a guy who was like, "Yeah, I've heard about Cassandra. That's such a shitty database. It doesn't have joins. Search possibilities are so limited. How it happened, what people still using that? That's a very bad database." I was like, okay, what are you using? Well, I'm using Postgres. And Postgres is a good database. Yes, Postgres is a good database. Yes, sure, Postgres is a good database. Like, I'm not doubt this question. I know it. I like Postgres. There are joins and cool search capabilities and all these kind of things. But tell me, please, dear sir, what's the biggest pressure on your database? Like, how many queries per second do you execute with your Postgres? He was like, okay, maybe 5 to 10,000 requests per second. And what was the biggest, like, most powerful Postgres deployments you ever heard? Like, how many queries per second they perform? Well, clustered Postgres was capable of handling some around some dozens, thousands, or hundreds thousands of queries per second, I believe. When we speak about Cassandra, we speak about literally dozens, millions of queries per second on a single cluster. It's a specialized database to answer those requirements. Yeah, so thanks, David. Let's move on. So based on those requirements, we can speak about architectural decisions. As architects, we design decisions or make decisions based on the requirements we just formalized. And first answer, we need to have multiple active data centers um, working together. So we need to have basically data center per each continent, or maybe even more, to have data close to our customers, so we can answer responses quickly, questions quickly. But meanwhile, it helps us with high availability, because even then there is a real disaster and region is wiped off, we still can work with the customers using different data centers. Now, to answer volume and velocity questions, we have to partition our data. We need to split our data into chunks. That means there are no single server capable of handling dozens, millions of queries per second. We have to distribute this workload over multiple servers, and Cassandra is a distributed database. So that's exactly what it does. It partitions data over multiple servers. It helps us with scaling. It helps us with basically handling any data of any size, petabytes and petabytes and petabytes. Now, SLA on response time. How do we ensure we are always dispatching quick responses? First, we will have to do denormalization we discussed today. And second, we will need to have partition-based routing. I will not stop on that right now, but you will see my explanation in half an hour. And yes, thank you, David. Can you please voice it in the...
Yes, you absolutely must understand partitioning to understand and effectively use Cassandra. It's absolutely key to the way Cassandra works.
Correct. Yes, that's totally like, if you hear someone saying, oh, but Cassandra is slow, you can just, without even any further knowledge, just tell him or her, you have your data model done wrong. Boom. And 99% of the cases, you will be right. That means people don't understand partitioning and they take off their airplanes without learning how to fly and how to land. Good.
Yeah, I came out of our services group, and the number one issue we have working with customers who have issues is it comes back to data model, data model, data model.
Mm-hmm. Yep. Always like that. By the way, I was curious, David, if we combine our common experience, your experience and my experience in software development or in IT field, like how many years we will have for two of us? I bet around 40 or more.
I have over 30 on my own.
Okay, and I have around 20 on my side, so we have overall half century of experience in information technologies. That's quite some number, right?
Yes.
Okay, funny. Good, let's move on. And finally, service level agreement on high availability, SLA on HA. If you need to have your data highly available all time at all costs, you definitely need to think about replication. And replication means your data, every single piece of data, and store it in multiple different places. That basically like a backup, but backup usually you write, put it on somewhere on disk and put it onto your storage place, whatever. And replica means live replica. It's attached all the time and available all the time. So if something happens with a first source of data, clients can easily switch to a replica, to another replica. You will see it in action in a moment. And then finally, decentralization, we discuss very soon. I don't want to stop on it right now. But you see, that's a very important process. We are switching from four requirements we have on distribution, volume, time, and availability into some architectural decisions we did based on these requirements. And that's a very important process. Good. Now, there is one more thing I want to say. One of the reasons relational databases were totally owning the market of databases was because they're general enough. They're multi-purpose, jack of all trades, master of none. They can play a little bit on both sides of a data field. What's this field about? On the left side of the field, there are OLTP databases, so online transaction processing. On right side of a field, there are OLAP, OLAP, online analytical processing, and those are very, very, very different. Let me explain, please. But by OLTP databases, we usually mean databases for handling workloads, or we mean just workloads without any databases behind them. Those are customer facing in most of the cases. We have a lot of operations per second, if we speak about big companies, of course. And we have very strict service level agreements because your customers will not wait for you to recover from a downtime. They will go to your competitor. And we don't want it to happen with your business. So that's why we are talking today about Apache Cassandra. Now, yes, that's usually a lot of operations, and we require them to be very, very fast and always available. On the other side of the field, we have online analytical processing. That's about exploration of the data, about the analysis, about our analysts, marketing people, I don't know, sales, doing some analysis of our data we have and thinking how to improve our interaction with customers, how to grow our business. And that usually includes very, very, very complex queries, working with historical data, exploring customer behavior, or I don't know, exploring weather change in a region if we speak about some kind of a weather forecast system. So very, very, very different kind of things. Usually, OLAP workloads can take hours, in some cases, even weeks to be done. And that is perfectly fine because guys who are running them, or girls who are running them, or whoever running them, those are employees on a salary and they can date. They are not customers. Those are two principally different things. So relational databases for dozens of years were good enough on both sides, but requirements are getting stricter and stricter, and we have to perform faster and faster, or we need to do more and more advanced research and exploration over data. On OLAP side of things, it led to the development of data warehouses or data lakes specialized on data analysis. And on OLTP side of things, it came to the appearance of databases like Apache Cassandra, which is specialized to be customer facing very quickly. But Cassandra is not so good with complex queries, with like dozens of joins, for example. Well, there are no joins in Cassandra. It's non-relational database. Why no joins? Because we have petabytes of data spread it over 1,000 servers, as you will see again in a moment. So, as humanity developed from generalized state where everyone was a farmer, a hunter, a gatherer, a warrior if required. But meanwhile, we developed dentists, we developed book writers, we developed software developers. We took this way from generalization to specialization. Why? Because specialization is more efficient. And that's exactly the same what's happening with the databases. They're going this way from generalization, a little bit of everything, to specialization. One purpose, but when well done. So in the end, we are speaking about distributed, decentralized OLTP database. Distributed means it perfectly runs in multiple data centers simultaneously building a single cluster. Decentralized means what it follows, not traditional leader-follower architecture, how we formerly used to call it master-slave architecture, if this definition more familiar to you. But it's decentralized, it follows peer-to-peer architecture. Each node communicates with each node, and each node is capable of processing each and every query. Finally, it's mostly OLTP specific. And well, that's a database. It kind of means what it stores data, but I hope if you are here with us at this stage of a workshop, that means you kind of know what the database is. I hope. So what are the Cassandra biggest users for today? I would mention first Apple and Netflix. And actually, I love those guys because they are not just users, but also developers. Both of those companies, although they are competitors in real life for some parts of the businesses, they still work together developing Apache Cassandra because Cassandra is an open source project. Last year, Apple reported what they currently count more than 300,000 database servers with Apache Cassandra, storing hundreds of petabytes of data and dispatching millions of queries per second. Netflix, I love those guys because they are even more open. They provide us more data about how they use Cassandra. By the way, if you are interested how Netflix uses Cassandra, we have a special recording available at dts6.io/Cassandra at Netflix, where a cloud database architect from Netflix, Vinay Kumar Chellam, tells on how they use Cassandra at Netflix. And like that was a very interesting talk. I organized Cassandra Day India a couple of years ago, and Vinay joined us and shared his experience. It was just great. So they reported what on their single most active Cassandra cluster, they handle 30 million operations per second. And this number actually scares me because that's really a lot. Good. So let me ask you a question. And that's going to be first question. So please get to your main team and tell me, Cassandra is the best fit for OLAP workloads, OLTP workloads, both types of workloads. Yeah, I see people answering. Cool. Keep your Menti close to you. I will keep asking questions, so don't miss. And David, thank you for the link to Cassandra at Netflix.
I thought you were thanking me for saying some of us, like Alex, were wizards.
Yes, definitely. Well, and you know, wizards are never late. Yes, correct answer is Cassandra is best fit for OLTP kind of workloads. For both kinds of workload, pure Cassandra will not be a good fit because you cannot run really complex queries over Cassandra, plain Cassandra. You attach, for example, Apache Spark on top to read data for Cassandra and run even SQL queries over SQL database. It's technically possible. That's not vanilla Cassandra, right? That's extended using Apache Spark, for example.
Right. And if you go back to
Yep.
those, sorry, Alex, if you go back to those four things Alex highlighted, geographic availability, high volume, time SLA, and availability SLA, that really fits that OLTP environment.
Yes, yes, that's mostly about OLTP. Cool. So, question asked. So, finally, most important things and most important features you need to know. Cassandra is really ready for big data. And then I say big data, I mean data what doesn't fit single server, like really doesn't fit single server. Cassandra is a good fit, then you need extreme read-write performance. So when you need to handle more and more and more and more queries per second, that might be a good choice for you. Cassandra is famous for its linear scalability. What that means? It means basically it introduces zero overhead on adding more servers. Cassandra scales horizontally, not vertically, by adding more servers to the cluster. And that's a very interesting research done by Netflix, where you have their test environment scaling from 50 servers to 300 servers while measuring amount of writes per node. Notice I'm speaking about writes. Many relational databases scale well when we speak about reads, because following this leader-follower architecture, you can always add more followers and you will be good. But how do you add more leaders? How do you add more master servers? That's not going to be easy. And
Right.
they speak about write scaling. Yeah, David?
Yeah, in those databases, if you look at this curve for writes, you'll see that the curve eventually stops rising steadily and starts to level off relatively quickly. So
Yes.
that's why we talk about that linear scalability. It's huge when you're talking about huge write volumes.
Yep. So basically, for most of the databases even capable of scaling at all, this line would be somewhere here and not straight like with Cassandra. So we basically scale it up their cluster from 50 nodes to 300 nodes and look at the results they got. That was a really great job. And by the way, again, many thanks to Netflix for this support and for this like work proofing how it scales. That's important for us. Very important thing. And yes, Siva Kumar, we do can say Cassandra is really good for write-heavy applications. Really good. There are some limitations coming. So there is no silver bullet. There is no perfect database. If someone says you what Mongo is a perfect database, or Cassandra is a perfect database, or whatever, Oracle is a perfect database, like be careful. This guy is going to sell something to you, right? Uh, it all depends on your use case, and there is no silver bullet. Good. So please notice, like David, getting back again to your mark you recently did, please notice this asterisk. You know, when you have this mark in your contract or in your, I don't know, mortgage papers, whatever, you need to pay a lot of attention to text in small font somewhere down, right? There might be some tricks. The real trick is this feature works only if you have your data model done right. And that's what we teach on our free DataStax Academy course at, well, DataStax Academy. But let's keep going. Finally, highest availability. So we have multiple live replicas with multiple data centers. That means what the same piece of data can be in Mumbai, free replicas, and Frankfurt, free replicas, and Boston, free replicas. That means what outage of a single node never lead to outage of the cluster. Even outage of a full data center never lead to the outage of a cluster. So if you cannot reach desired availability with Cassandra, basically you cannot reach it at all. It's the most available database in the open source field at the moment. Now, we can speak about 100% uptime. There are companies where our clients who reached this 100% uptime over years, and they're perfectly happy. Biggest problem with big companies, they never want to share their names, so we don't know really. So we cannot share like who are those. Good. Uh, Now, operations over a cluster of thousands and dozens, thousands, even hundreds of servers may be very painful. So but my favorite part here, as I'm a very lazy engineer, I believe that only lazy engineers are efficient enough. What Cassandra cluster is smart and execute many operations on its own, and I don't have to. You will see those self-recovery capabilities soon, and I don't have to do it manually as on my own. It's just many of operations done by a database itself. That is just amazing. Geographical distribution is already mentioned, but let me highlight one more thing. We often speak about geographical distribution for our databases as well, but for most of them, it will be active passive. So one data center is active. You can both write and read data from it. And our databases are passive or standby. You can only read data, but write data you still have to the active data center. With Cassandra, it is different. With Cassandra, all data centers are active. So you not only, being you in California, you not only read data from a Californian data center, you also write it here, not in the Indian or Chinese data center, of course, because obviously it's going to be slow. And finally, it's not bound to any platform, so you can run it anywhere, any cloud provider, your own data center, so AWS or Google Cloud, doesn't matter. Why? Because it's vendor independent. Originally, it was developed in Facebook, but after that, after some adventures, it was contributed to Apache Software Foundation, which you know for sure, or at least know its products. It's an open source foundation, what is famous for Hadoop, Spark, Kafka, Zookeeper, Maven, and many, many, many other projects. Good. So now here comes some pain, because there is always price to pay. Joins, no joins. And people be like, what do you mean no joins? I want to join data from multiple tables. Don't forget, we are speaking about geographically distributed data with hundreds or thousands of servers. And like joins don't work in such environment. Okay, they work for some databases, but it's always, always, always going to be extremely slow. Cassandra is designed to be fast. Working with data, you must always know the partition key, and you will see it soon in action, so I will not stop there. It has pretty limited search capabilities, and that means if you are going to do search over your data, you are going to do some more work, like using maybe Spark, maybe using additionally Elasticsearch over Cassandra. There are some ways to do that, so these kind of things. And it requires qualified personnel. So if you are not if you don't have like engineers ready for that, you really better send your people to DataStax Academy to get proper training, not short workshop, but real training.
And Alex, I want
Yep.
to jump in something in the slide. It says very limited search capabilities. When I first learned about Apache Cassandra, I saw that and I thought, well, isn't that what a database does? And my response to that today is Cassandra has very powerful query capabilities because it allows us to tune a data model or custom build a data model to support certain queries.
Yep.
But if you want to do ad hoc searching beyond those queries for which your data model was designed, that's a challenge in Cassandra. So it's definitely tuned for high performance queries,
Yep.
but not generic searching.
Yeah. So there is a way to get good search capabilities with Cassandra, but that will require some pretty a lot of play with data model, a lot of denormalization, and it will fit some particular cases, but not all of them. Good. I see an interesting question. Aprianto Tobing asks, how with Scylla? Scylla is an startup attempt to reproduce Cassandra's success following the same white paper. Um, it's a single project. It's a single company project. And project what basically implemented, I believe, like 10 or maybe 15% of Cassandra capabilities, but claims to be equal. My test shown it's not equal, even close. So if you want to trust your business success on some startup company, which maybe not get enough funding tomorrow and basically stop any kind of maintenance and development of a database, so you will have to do it on your own. And with decentralized distributed solutions, this kind of work requires very, very expensive software engineers. Then good luck. I prefer to stick to um, open source, original, what is developed by Apple, Netflix, Instagram, DataStax, of course, and many others. Let's go. How does join affect performance? That's a good question by Amin, so let me answer. Joins per se affect first. Join do affect performance. Then your node server, relational database server, execute join. It needs to gather and intersect a lot of data basically in memory. That's pretty expensive operation already. But what I meant is what actually uh, then you have some pieces of your data distributed across hundreds of servers. For each next join in your SQL statement, you will have to gather this data in a single place and process it and do it again and again. So each and every join over distributed data is definitely going to be extremely slow and make node executing it busy. So people, let's keep coming. Let's keep questions coming, and that is the next question. So tell me, I mentioned that briefly, and now I'm interested if you was listening thoroughly enough. How to scale Cassandra cluster? By scaling up, so vertically upgrading servers, scaling out horizontally, so adding servers, or Cassandra cluster does not need any scaling. What will be your answer? Oh, yes. Hey, take a look, David. Looks like we are getting our salary this month, right?
Yeah.
Yes, scaling up is a traditional upgrade for traditional scaling way for relational databases or for single host or leader follower databases, because they don't support horizontal scaling. Horizontal scaling helps you to scale much better because to a cluster you can add more and more and more and more servers, while vertical scaling, so upgrade servers, scale up, getting prohibitively expensive. Very soon, it requires downtime of a cluster. In Cassandra, scaling is downtime less. It's a live operation, so database stays available all the time. Cassandra, and two people answered Cassandra cluster does not need scaling. Thank you. Apache Software Foundation community likes your mood, but that's not correct. No, there is no silver bullet. Cassandra cluster totally can require scaling, that's for sure.
And given when Cassandra was released in open source, it was very prescient of Cassandra to rely on horizontal scaling because shortly or around the same time Cassandra came out, we had this revolution in cloud-based services where horizontal scaling is really, really easy. You just fire up more instances in the cloud. So it fits this cloud model perfectly.
Mm-hmm. We explain it in details very soon. Good. So we are going to talk about some holy grail, some of the most important things of how it works finally internally. And the first rule we need to know is all servers are created equal. That's very important and very unusual to people with pure relational experience, pure relational background, because most of the databases and NoSQL, many NoSQL databases as well, like Mongo, they follow leader-follower architecture. To the leader, you can read and write. To a follower, you can read only. That's logistically most convenient architecture. It's easiest to develop from a database point of view. Like people who develop databases, it's easiest for them to develop, but it introduces some limitations. First, it's single point of failure. If anything happens with your leader server, you are not going to write any data. It's hard to scale for writes. You always can add more follower servers, but if you need to scale for writes, if you are getting too much writes, you are getting more and more customers, you will have more and more writes, then the only way for you to go for it is to a vertical scaling for leader server, which is expensive and which includes downtime and all the other things I already mentioned. And finally, application needs to know where to write. If you will attempt to write a request to a follower server, you will get an exception. That doesn't work this way. So Cassandra follows different architecture. It's masterless or peer-to-peer. There are no single point of failure. Each node is capable of processing writes and reads. And well, If node is down, then your client, your driver, will just switch to next available node or maybe even next available data center, depending on the situation. So application can contact any node because any node is capable of processing every request. Notice, it doesn't mean what each node stores all the data. Very common misunderstanding. Of course not, it's not possible. So no, each node is responsible for the part of data, as you will see soon. Question. Get back to your phones and try to make me right answer. How many master nodes for a Cassandra cluster we need to have? Minimum three per data center, count of follower replicas divided by three, or no master nodes? Okay, I see you answering faster and faster. That is cool. Thank you for everyone who joined. And yes, no master nodes. There is no concept of master nodes. You see, even after us being speaking about the masterless architecture for a long, long time, there are still people with relational background who cannot accept this idea, like their minds tries to resist that. No, people, there are no master servers in Cassandra. No, at all, not a single one. It doesn't exist. That's a true democracy, and everyone is equal, you know. Good. So, getting further. Now, my favorite part what always brings the biggest amount of misunderstanding. Uh, and meanwhile, there is a good question by Siva Kumar. Does Cassandra needs a specific client? Yes, like you work with relational databases using normal drivers, like Postgres drivers for Postgres, for example. Then exactly you work this way with Cassandra. You just need Cassandra drivers, were, by the way, mostly developed by DataStax. Let me check some stream stats. Yeah, we are looking good. So let's
And also,
proceed.
Siva Kumar, I might add that
Mm-hmm.
there is another open source project called Stargate
Mm-hmm.
to use REST, GraphQL, gRPC, and a number of other ways to access Cassandra without going through a language specific driver. So
Mm-hmm.
ways to get to Cassandra. But I'll share the link for that open source project.
Yep. Perfect. So now please pay attention because this part is very important. Like that's a very internals every person working with Cassandra must understand. Data is partitioned and that is the game changer. You totally must understand that if you are going to work with Cassandra. Let me explain this idea based on the real example, based on some real data. Imagine we have a lot of temperature sensors deployed in multiple different places. In this case, for example, in the United States. So we will have each sensor records temperature, and each sensor belongs to one network. One network can have multiple sensors. One sensor belongs only to one single network, so it's one-to-many relation and each sensor records temperature. Cassandra works with tables, so we can take a look at this table definition. We are going to create table, sensors by network. So network will be some text, some ID. Sensor ID will be also some text. And temperature will be integer. Actually, it should be mostly probably float, but let's simplify. So we see we have table, sensors by network. Network, sensor temperature, and some states, for example, some network names, some sensor IDs, some temperature recordings. So far, so good. Now, we have this table on the right, and we have 7 servers in our data center. How this data is going to be stored internally? In relational databases and in many of NoSQL databases, you will have these data copied everywhere, like each table is in full present on all of the servers, as long as you don't use sharding, but sharding is out of scope for today. That's how it looks in Cassandra. In Cassandra, data is organized in distributed tables. So each um, so pieces of those table will belong to different servers. It gives you huge power. It means what you can store more and more data over more and more servers and still be able to answer a query within single-digit milliseconds, answer extremely fast. And don't get me wrong, it also brings a lot of problems to you because when this partitioning, distributed partitioning, is also can be pretty painful. Now, if we want to search, if we want to run search, for example, find a sensor which currently has temperature, for example, 45 degrees, how many servers would you ask with this question in a small to medium data relational database? You will ask one and only one server, right? So it's going to be pretty cheap and fast operation. Um, then if we have this distributed table and we want to find all the rows, all the sensors stored currently having 45 degrees, we are going to ask this server, right? So we get the answer, but also we are going to this one. Maybe in Idaho, there are also sensors with a temperature 45, by the way, 210. Something is really bad happening in Idaho. Then Georgia and Hawaii, we have to check too. Maybe Florida, maybe Delaware, maybe California, maybe Alabama. Who knows? We have to ask literally every server in the cluster. And that's called full cluster scan or full table scan. And if you think it must be very slow and inefficient, you are perfectly right. It is slow and it is inefficient. Pau has awesome answer. What if a Kansas server is down? You will see in a moment. We answer that on the very next part very soon. That was a good question, sir. Or madam, sorry, I don't know. Okay, so that's how data is spread. Okay, but data is spread how it happens. We know why, for scaling, for capability, for performance, for the greater power. But how it's happened? It's happening based on the partition key. You remember this part? I intentionally skipped something here, but now let's take a closer look at it. There is a primary key definition, and primary key, first part of a primary key always will be partition key. And this partition key decides how data will be distributed. So in this case, you see one partition, 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 another partition. Notice what each server is capable of handling of a lot of partitions, of course. So there can be many partitions neighbors to each other, and that's perfectly fine. If we would arrange data differently, like based not on the network, but for example, based on the sensor ID, what would happen? We would have as many partitions as many sensors we have, and they will be distributed totally different. If we would partition our data based on temperature we are currently recording, that's going to be messy because like their partition key going to change pretty quickly as soon as temperature changes, sun rises, and that's going to be a totally different story. But for our purpose, we design it with partitioning based on network, and that's why our table name is sensor by network. And then finally, a last layer of how it works underneath the hood. We have this table on the left side. Alabama, sensor ID F001 with a value 92. How it works, how data is being distributed to server A, not to server B, for example. There is a special mechanism called partitioner. Partitioner, modern partitioner in modern Cassandra, in modern DataStax Enterprise, in AstroDB, works using murmur-free hashing algorithm. I really love this name, murmur-free, like some cats murmuring while hashing my data. I love it. So this partitioner takes whatever value you give to it and converts it into integer value. So for example, if we give to it Alabama, it becomes 59. Or if we give it Idaho, it becomes 12. Hawaii, okay, 45. So hashing, you might hope you know what the hashing is. Now, interesting point. Each server in a data center is responsible for a range of possible tokens. So partitioner generates tokens, integer values for us. 59, 12, 45, and so on. Those are like usually huge numbers. You usually don't see partition token 59. It's going to be long, 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 long integer. And each server is responsible for a range of tokens. For example, if we have 4 servers data center, each server will be responsible for approximately a quarter of your token, of all possible tokens. So we speak to 1 to 25, 26 to 50, 51 to 75, and so on. In this case, with 4 data centers, 4 token ranges. Okay, so far so good. I see David answering a ton of questions. Thank you for asking. Uh, and then we can easily realize what if that's Alabama, partition Alabama, going to be token 59, then token 59 belongs to the server which is responsible for token range which includes 59. 51 to 75 includes 59. Then we go. Idaho, so 12 goes to a first server. 45 goes to a second server, and fourth server stays lazy and empty with no data for the moment for this 6 record table. Let's move on. Why partitioning? What is big data? There are 100 of different definitions of what the big data is, and they are huge and clunky, and like I don't really like them. I'm a simple practical guy. I solve problems and getting my money for that. Best big data definition I ever met was developed by me. Sorry, but yeah, I believe that's right. Big data is a data what does not fit to a single server. And by splitting it into chunks, we spread these big data over multiple amount of servers, getting it's highly performant. So even though when you have billions of records and petabytes of data, you still get select statement and get your answer very quickly. Doesn't matter if you are in Africa or if you are in the United States or in Australia. So that is a real power. How works scaling with Cassandra? How do we feed more data or how do we process more queries? Imagine we have 4 nodes data center and each node responsible for quarter, so 25% of all possible tokens. And we know what Black Friday is coming, or for example, it's Netflix and we are releasing last episode of Game of Thrones and we are totally sure what everyone will be watching that. Okay? So we go and we scale out. We add one more server. Then happens a process called a token range recalculation. So cluster recalculates. Now we have more servers. That means each server is responsible for smaller amount of data. As a result, we assign new token ranges or part of the old token ranges to a new server, stream data from old owners to a new owner, and boom, now we have less data per each server, less queries per each server, and we can process more customer queries or we have more disk space depending on what our current situation is. Now imagine we don't need it anymore. Black Friday is gone, or we just dispatched last video of Game of Thrones and everyone is unhappy, everyone is angry, no one is watching Netflix anymore. What's going to happen? We are not going to pay extra for the servers we don't need anymore. That means we need to do downscaling. And we tell to a cluster, we don't need those those 2 servers anymore. Now you are to downscale and to decommission 2 servers so we can save money on our cloud costs, pay less for our servers. Okay, so now you know what's going on. Token range recalculation. Cassandra cluster recalculates token ranges and puts more data on each server, streams it back, and we can take off 2 servers after some time, so let cluster time to stream data back. And biggest and best part of it, first, all scaling operations are automated. So I just tell that's your new server, join cluster, and all happening automatically. Or I tell like I'm going to decommission the server, so get off the cluster, I don't need you anymore. So I can kill this server very soon, and it's totally fine for a cluster. I just need to let it time to stream data back to ours. Then all scaling operations are live. So scaling operations on many databases incur downtime while database does not answer any requests. Cassandra keeps those live and requests are being dispatched still. And that is really cool. And finally, yeah, it's, did I say that again? Yes, I did, but still, I love it. It's automated. So I can launch per process and go drink coffee, go watch a movie, and Cluster does it for me. Like I say, I'm lazy enough. Token ranges definition is totally automated. Yes, you can have control over it, but you better don't. Really better don't. Cool. So time for question. Question number 5. Jump to main team. So, oops. No. It's early. Sorry. Okay. Yes, I made this question too early. Let's speak about the last part before we go to hands-on part. Data is partitioned, what gives us scaling capability. But that's not enough because now we can have a lot of data, but if something is broken, then that means we still will be downtime for at least part of the data. How do we address that? We do it with replication. And first thing you need to understand is replication factor. Replication factor means number of servers what will be used to store each partition. Then you create a key space. And key space is basically like a schema in Postgres, for example. Each table belongs to schema or each table belongs to key space. Just logical group of tables. Then you create a key space. You must define replication. And there are plenty of options, but one you really must specify is replication. All the other have some reasonable defaults. And replication, we must define replication class and replication factor. With replication factor, it's very easy. You just specify data centers you need to have this data and how many replicas you are going to have in this data center. By the way, I really like asking questions here. Please tell me in YouTube chat how many, if this statement is correct, how many data centers I have in my cluster. And little hint, that is a tricky question. But please still give me a number. What do you think? How many data centers I have in my cluster? Try like there. Shoot. Try to guess. 2, 5, 5, 2, 2, 8, 8, 3, 2 data centers. Anyone? Okay. Yeah, that's a tricky question, people. Minimum 3 for us, minimum 5. Oh, no, I'm Leila, I'm asking not about servers, but about data centers. Data centers on the left. So regarding the right part, you would be right, but I'm asking about data centers, but thank you, yeah, it was close. So, okay, people. Artyom. I'm sorry. Artyom is the creator of a data modeling methodology. So basically, he is one of the best Cassandra experts in the world. And Artyom, please notice, I said if this statement is correct. So I support here, I expect here. Okay, right answer. Thank you. Right answer is, well, number is definitely going to be somehow n, but what n is n? If the statement is correct, if the statement is right, so it's going to be executed, that means what I have at least 2 data centers. But please notice at least, that is important part of the answer. Because, for example, I might have dozen of data centers. And still, if I have a dozen of data centers, I might not need this data, this sensor data, on any other than those 2 data centers. If I don't need my data there, I don't specify them there, and no data of this key space, no tables belonging to this key space will be deployed on these data centers. So people who speaking about 3 and 5, that is a count of the servers I'm going to have in my key space for this data. So that means what? Mostly probably I have at least 3 servers on United States West 1 data center and at least 5 servers on Europe East 2 data center. Although there is no simple answer because there are some adventures can possible, but the right answer is 2 or more if the statement is correct. Cool. So with replication factor 1, each server in your data center going to store partition. Only one server will be responsible for partition. Replication factor 2 means what each partition is stored on 2 servers. And replication factor 3 means what each partition is stored on 3 nodes. And usually we do not recommend to go higher than 3. In some exceptional situations, you might want to have 5, for example, but that happens pretty rarely. Now, joining those two ideas together, replication and partitioning, how do those interlapse? Technically, internally, yeah, nodes are servers are the same thing in Cassandra terminology. Sorry for, yeah, it's cool. So then we have replication factor 1. Each server will be responsible for its own token range. When we have replication factor 2, each server is going to be responsible for its own token range plus token range of its neighbor with replication factor 3 of 2 neighbors and so on. So that's how it works. And so internally, with replication factor 3, when data arrives, this server gets this data and it sees what it's not responsible for the token range this data belongs to. So for example, we know what partition partition key forest becomes 59, for example. That means what we will work with those 3 servers, but this request is processed by this server and it's not responsible for this token range. It's not responsible for this data. So that's totally fine. Each server in the cluster, actually even your driver in your application, understands token ranges. It's called a token aware. Because of that, this server will dispatch your data to the proper servers because it knows them already. So execute those 3 asynchronous calls, deliver data to those servers, and then operation is done. During this operation, this server is called query coordinator. It means what it coordinates operations, so writes, for example, for this query. But each server is a query coordinator. Again, if that server will get this update, then it becomes query coordinator. If this server would get this query, it will become a query coordinator. So that's how it works. Good. Yeah, so that was I was just talking about. Each Cassandra node, each Cassandra driver understands data allocation in the cluster. It's called a token aware. Application can contact literally any server and still get the answer. If server is responsible for your data, that's cool. If server is not responsible, it knows who is responsible and it will execute coordination. It will get this data for you from its neighbors. In normal circumstances, driver will contact replica node to avoid node responsible for your data because driver is token aware, so driver will get data properly. Good. And David, it's your time.
All right, so we're going to look at the hands-on portion.
Mm-hmm.
And I guess, Alex, you need to switch over and display
Yes, let me switch to your display. Give me a second.
Sure, and as we get started, I'm working through the lab exercises from DataStax.academy. And you need to look up this course, which is under workshops. It's called W001 Introduction to NoSQL with Apache Cassandra. I'm going to run through some of this pretty quickly. And this is all the introduction if you were looking at this course on Academy without following us on the video. But the first thing we're going to do is create an instance of AstraDB. We haven't talked about AstraDB much, but AstraDB is DataStax's hosted Cassandra in the cloud. And I will tell you, those of us who work at DataStax, I have access to Cassandra on my desktop. I have access to Cassandra in Kubernetes, Cassandra in Docker, Cassandra in every possible form. But if you ask me to very quickly kick something out or test something in Cassandra, I go to Astra and fire it up. It's real simple. And I use the same free account that you do. DataStax doesn't have my credit card, and I get a pretty good chunk of usage free each month. And you do have to register, but there's no credit card involved. So from the Academy, I'm going to click on this link, create AstraDB.
And also this link is just pasted into the YouTube chat.
Yeah. And now I'm going to sign in. I already have an account, so I'm going to sign in with my DataStax Google account, and that will bring me to Astra. And if you look, I'm concerned about databases. There are no databases currently. So if I click, there are no databases. So I'm going to create a serverless Astra database. And the parameters for creating that database are here in Academy. The database is going to be called Workshops. It's going to, the key space we're going to create, and a key space is a grouping of tables and a few other things. That's called sensor_data, and we're going to create it in the Google Cloud. So workshop sensor_data, Google Cloud, and here are the regions that are available to me, the ones that aren't shown as locked. And I'm actually based in Iowa, so I'm going to choose Council Bluffs, Iowa.
And just a little notice, if you was with us on one of our previous workshops, then basically you might have this database workshops already, and that's perfectly fine. So you will just have to create a new key space.
Right, or you may have to resume the workspace in case it's gone to sleep. You'll notice now the workshop database is pending. It takes a minute or two to create. While we're doing that, let's take a look. Here is the Connect tab that shows you a number of ways to connect to your database. To start with, you can generate a token that gives you the credentials and the information necessary to connect. You can get a secure Connect bundle, which also includes the TLS artifacts you need to connect from an application. You can install the Astra CLI, which includes our CQL shell to run commands on your desktop. We're going to run them in this web interface. And you can look, there are other ways to access it. There are various APIs. I mentioned Stargate. Stargate is a facade that sits in front of AstraDB or Cassandra. You can run it locally, and lets you use a document API to use JSON style access, a GraphQL API, and we talked a little bit about GraphQL, as well as a REST API. So if you have an existing application using one of these other APIs, you can certainly use it with minimal change to access Cassandra. And more about, lots of examples and ways to connect with the different APIs here. The workshop the workshop database is still starting up. Some of the other tabs here is the health tab. Once the database is active, you'll see a number of graphical displays having to do with database health and database performance. So it does give you some monitoring. The CQL console, we'll be spending time there, so I'm not going to focus on that, but that will allow us to execute CQL commands. And I don't know if we've said, but CQL stands for Cassandra Query Language. And it's very similar to SQL. Unfortunately, it sounds a lot like SQL. So you may hear me slip and say SQL, but I really mean Cassandra Query Language. in this context. And it's the way you interact and run commands against the database. CDC, part of AstraDB, or excuse me, Astra, in addition to the database, is we have a hosted Pulsar service, so we can do change data capture and streaming, a lot of other cool things. So our workshop database is active, and now you can see here are some statistics. We haven't done anything with it, so there are no latencies and requests and all of that, but it gives you an idea of some of the things that are available. All right, so let's go to the CQL console. It's going to connect, and what we're going to do is we're going to explore the key spaces. So we're going to go in and describe the key spaces that are already there. Now, you'll see we use the describe command. There is code completion here, so I said K and press tab. And this shows the key spaces that have been created. Notice that we created the sensor data key space, but there are a number of other key spaces that are all prefixed with system or data stacks. Those were there automatically or automagically. So those are the system key spaces and our sensor data key space. Next thing with a key space, you need to use that key space, just like you would use a schema in a relational database. So I'm just going to copy the use command and use the key space. All right, that's exercise one. Pretty simple. Connecting to AstraDB, creating a database in key space, and using the key space. It's all spelled out on DataStax.Academy. So, Alex, I'm going to hand it back to you.
Give me a second.
Sure. And there was a question about certificates, coupons for the exams. And yes, you can receive a coupon for this exam, but would strongly encourage you to take, we have two certifications, an administrator certification and a developer certification. And at DataStax Academy, the administrator certification, the prerequisites are DS-201, which is a much expanded version of this content, plus DS-210, our admin-specific content. Once you've completed those two classes, or for the developer, DS-201 again, and DS-220, which is the in-depth data modeling, once you've completed either of those two sequences, you are eligible to receive a voucher good for 2 attempts at one exam, or if you do a great job, and I know you will, and pass the exam in the first attempt, you can use that same voucher for the second exam. But you would be advised to take the courses at Academy first to be really prepared to take the exam.
Yep, perfectly tabular. I see some people of experience here. That's great. Cool. So I'm switching back to my screen and I'm going to ask you a question. So get back to your main team. And my question is going to be, what is the biggest problem of replication? And that's going to be this question this time. What is the biggest problem of replicated data? Increased disk space consumption, more network transactions because data is spread across multiple servers, or potential cross-node inconsistency. Again, as all of my questions, this one is tricky. Yes, and sure, we can post the, yeah, wow! People, you are doing great, actually. Normally, most of my students not doing so well here, so we really got some people of experience. That is great. So, notice the part biggest problem. Replicated data indeed leads to increased disk space consumption, but you know what? Disk space is cheap, reputation is priceless. Okay? I like most of the companies using Cassandra, so big companies normally can afford buying more disks, but cannot afford downtime. So that's exactly like Cassandra use case. More network transactions. Yes, it is a problem, but again, currently even SDNs, even software-defined networks are still very fast. So it's kind of again a problem you can leave that. But potential cross-node inconsistency is a really, really big deal. So let me show you something. Mm, yes. What is potential cross-node inconsistency? When they are changing a value and data is replicated, one of the nodes storing this data, one of the replicas, might not get the update. That leads to the situation then one node stores outdated stale data and others store new data. That is not about Cassandra. That's exactly the same about every distributed system more than single host system. You introduce caching, you can run into inconsistency problem easily. You introduce distributed caching, you are going to run into this problem one day or another. So like I can tell that's like quite a big deal for every kind of a distributed system. And of course, as Cassandra is used in banks, it's used in like, I don't know, health institutions, many different companies. That is a very, very serious thing. Yeah, and that's interesting point, David. Cassandra currently uses Paxos, but there are some huge upgrades are coming, and Paxos is going
Yes.
to be replaced. First Paxos version 1 is going to be replaced with Paxos version 2, which is happening right now. And then later, thanks to Apple and thanks to University of
Michigan.
Michigan, it's going to be replaced with Protocol Accord, which is a very interesting thing. Okay. Oh, good question by Amin. How does one not getting right operation happen? Oh, easily, thousands of questions, thousands of options. Network outage, so network link is broken. Node being in reboot or on maintenance or anything like basically whatever can happen and single update will not reach the node response replicant. It's totally happening. You see, when you have thousands of servers and millions of operations per second, it's just a question of time something bad will happen. Good. So, as this potential inconsistency is a huge problem, like the biggest problem of replication, we are going to address this problem very, very, very seriously. Cassandra has layered defense to be able to protect itself from these kind of issues. And first layer of defense is going to be so-called hinted handoffs. What is hinted handoff? Imagine the example we discussed already. A query coordinator dispatches updates to our servers and sees what two servers returning confirmation acknowledgement, I got your data, tutto bene, everything is great, we are good, it works. And then one of the servers does not respond. We don't know what happens. We don't know what went wrong. Maybe power outage, maybe network outage, maybe server is too busy. I don't know. Maybe some aliens stolen this server. Everything can happen, especially if you host your data center in New York. Like you watch the movies, something bad's happening in New York all the time. And then query coordinator stores so-called hint. Hint is a persistent piece of data. It's stored on disk. It will survive reboot. In Cassandra cluster, servers are gossiping. They're communicating with each other all the time. And then the server sees what its neighbor recovered. So there is a gossip, what server, what was outed, now returned, server number 7, let's say. Then query coordinator will dispatch this hint to the message, to server what missed the update. And that works totally, completely, absolutely automatically. Automatically, I better say automatically. That means What I do not participate in this situation, and still consistency is recovered. It might happen deep at night, and as an operations guy, I won't even get a phone call or pager duty, whatever, invocation, come and fix our system. System fixes itself, and that is totally lovely. Good. But you know what? That is not enough because in some cases, still something might happen with query coordinator with hints. Something else might happen. So actually, as a layered defense, we are going to have multiple layers, more than this. First, one, hinted handoff is a Cassandra job. You don't have to worry about that. Then repairs is an administrator job. And this workshop is for developers, so we won't speak about repairs too much right now. There is a repair on read, which is again Cassandra job, so you don't have to worry about that a bit. Like that's totally automated too. But thing you really need to understand is consistency level, and that is a developer job. So that means you are going to learn it. So we go to CP theorem, one of my favorite parts and one of the most misunderstood parts. Now, if you are tired, I don't know, maybe it's a deep night at your place, please focus and refresh. This part is very, very important. So wake up. We are working. Stay strong. We are getting close to the end. CAP theorem operates three features: availability, consistency, and partition tolerance. What does that all mean? Availability basically means uptime. You ask a question, you get the answer. If outage leads to no response to you, so downtime, your system is not available. If outage still, if even in case of outage of a single server or a group of servers, your system still returns you response, your system is highly available. And that's the easiest, like everyone understands that. Now, consistency. Consistency in the terminology of CAP theorem means no stale data. You ask for something, you get the most recent value, punct, done. Like if you get some stale data, previously valid, but wrong now, your system is inconsistent. And then finally, partition tolerance. Partition tolerance is the most misunderstood idea. Partition tolerance is the ability of a distributed system to survive network partitioning. And most of the people on the internet don't get it. Most of the people on the internet thinks what partitioning is then group of your servers is not available at all completely. They are wiped out. Let me show you something. What is network partitioning? Imagine I have 6 servers data center. 1, 2, 3, 4, 5, 6. And there is a network partitioning in between of them. So my cluster kind of split it in a group A and in a group B. But all of those groups are available for the clients. So one client, application 1, instance 1, can contact this server, and application instance 2 on another server can contact this server. But in between, they cannot communicate. This server cannot reach that server. That is a network partitioning in the CEP theorem and in the database theory situation. So group A cannot communicate with group B. Group B cannot communicate with group A, but they both are available to customers. Really, so many people don't understand this point. If group B is completely isolated and unavailable, not available for anyone, is that partitioning? No, it's downtime for this group. It's a simple plain downtime. Doesn't matter if there is a power missing or network missing. They still cannot be accessed. They will be outdated, but they will not get conflicting updates. So real network partitioning is groups are isolated but available to customers, all groups. So partition tolerance is the ability of a system to survive network partitioning. With relational databases, it can lead to a problem called split brain, and split brain is a damn disaster. Imagine I have some disaster recovery scenarios, and imagine that is my master server or my leader server in this data center. And this group is isolated like that. What happened with group A? Master or leader, follower, follower, follower. Well, everything is fine. This group is operational. It's going to handle some more workloads because like we lost some follower servers, but still it will be operational. What's happened on this side? Those two servers, two followers, cannot reach leader server anymore. If they just stop processing any queries, it's bad, but that's not a real problem. Real problem, if I have some recovery plan, automated recovery plan in action, like failover mechanisms, I enable it. Not switch over, which is manual, but failover, which is automated. And for example, two of those decide what this server is going to be new master. And it becomes a new master as a result of an election, or leader server, sorry, and it gets all the updates. Now, two. So part of the updates may get to this one, part of the insert or updates can get to this one, and they will be conflicting because they may lead to different places. They're stored on a different servers. So when finally network partitioning disappears, you have a leader-follower architecture database with two leaders. Good luck handling this situation because like there is no automated way to handle that. You will literally spend weeks and months reading the logs and trying to recognize what the hell happened here and was these goods sold and delivered to a customer, this customer or that customer, because the data was isolated one from another. Split brain is a huge problem if there is a master node, correct? Yep. As Cassandra is masterless, then that's might be different scenarios. So it doesn't mean what you cannot run into problems with Cassandra. You can, that's for sure. I see David is smiling. Yes, but definitely there cannot be split brain problem because Cassandra handles this situation totally different, and there are no master servers. So,
But Alex,
yep,
let me jump
yes.
in. And with some of the side conversations about consistency level and replication factor,
Mm-hmm.
by correctly configuring those, you can choose which problems you are willing to accept and which problems, and under which case you're going to say, nope, I will not operate under this condition.
We will, sorry, we explain it just on the next slide.
Yeah.
Yep, so don't rush, it comes. Yeah, good question, by the way, who asked that?
Might have been Daniel.
Okay, thank you, sir, that's a good question. Good, so let's go. Now, finally, we discussed terms, definitions of that theorem. Now, what the theorem states, idea is in the distributed environment, we don't speak about single host database, we speak about multiple host database. In case of emergency, in case of an outage, in case of something goes wrong, you can have only two guaranteed qualities out of three. So basically the story is you, in case, then everything is green, servers are running, network is running, customers are happy, you somehow have both consistency, availability, and partition tolerance, but then shit happens, and that's just a question of time, as all we know. You have to decide, where are you going to be? Partition tolerance is something we cannot sacrifice. That's why people speaking about databases most commonly speak about so-called CP databases, so databases consistent and partition tolerance, paying the price of the availability. They are sacrificing availability to become consistent and partition tolerant, while other databases choose to be available and partition tolerance, here partition tolerant, by the price of the eventual consistency. Let me explain that a little bit better. If your database is available and partition tolerant, but eventually consistent, that means what theoretically you can get stale data, but you always get data. And now don't rush with your own ideas, but let me finish, please, first. That's very important to like miss one very important point. Some other databases choose to be consistent and partition tolerant. They reside here, and that comes with a price of availability. Like you always get the consistent answer, but you get no answer at all if in case of an outage. System tells you I cannot do that. Some of my servers are down. You are not getting. Maybe those servers store the most up-to-date value. I cannot check right now. You get no answer at all. Now, there is a very common misunderstanding. Is Cassandra AP or CP? And most of the people familiar with Cassandra say, of course, Cassandra is AP. That's what we have been told for years. And that is wrong. That is wrong. And now many people hate me for that, but that is wrong because the right answer is Cassandra is tunably consistent or configurably consistent. By pushing some buttons, by changing some configurations, you can travel in between and set up different approach, CP or AP, for different pieces of data you store. In any moment of a time, for each particular query, you can set desired consistency level you require to have. And that will lead database behavior for this particular query. So if you get the very same query, like in this example, we work with insert into product, some values. You can set consistency level for this particular statement. For example, in this case, I set consistency level 1. I will explain it in a moment. And then execute this query again, setting different consistency level. And execute this query again, setting different consistency level. And those queries will be executed and treated differently. Okay, now, what is the consistency level? Consistency level, as we work with replicated data, means how many acknowledgements we will wait, how many confirmations we need to get before we consider it insert or update operation as completed successfully, or read operation, what we gathered enough data to return consistent answer based on the current requirements. Each you see the story. Each piece of data you store, it might be of a higher importance or lesser importance thing. Like, for example, your very same application can work with your money and can work with your profile picture. I don't know, like Chinese WeChat, you have money there, messages, profile pictures, everything. Do you really care if you just changed your profile pic, but some people will still get your previous profile pic? Is it a disaster? No, I think you can survive that. But do you want your financial data to be consistent? Yes, hell, of course you are. So, of course you do. So that's the story. So changing consistency level for different queries working with different data, we jump in between different options of a CAP theorem. For example, with consistency level 1, we will wait only for one confirmation out of 3 replicas. Take a look, we have replication factor 3, so we have 3 replicas. But we have consistency level 1. That means when client executes query, query coordinator will execute 3 writes, 1 to 3 to all the replicas. But as soon as the fastest server answers, query coordinator will immediately return confirmation to a customer. Hey man, I got your data. Perfect. What's that? It's the fastest way. Because as soon as we get first reply, obviously the fastest reply, we don't wait for anything. We immediately tell to a client what we are good. But you know what might happen? Those 2 guys might be down, and client will never know what his update didn't reach those servers. So 1 is the fastest. Actually, only one consistency level is faster, which is any. So any, then 1, when we go to more advanced scenarios. Most used consistency level is quorum. Quorum means majority. Majority means for replication factor 3, it's going to be at least 2 servers. Easy as that. If we have, for example, replication factor 5, then majority will be 3. replication factor free with consistency level quorum is the most efficient, fast, and meanwhile economically reasonable way. So this way, having consistency level quorum, we can afford losing this node, store our data to 2 more nodes, and be fine. Even then this server is down, we still can read data and get data. And that is totally fine. And then finally, with consistency level all, we will require all acknowledgements for all replicas. And there is a very interesting issue. Think about that. Now, my data seems to be fully consistent, and I want my data to be consistent. All right, I bet you too. So you say, write my data with consistency level all, always. Is that a good idea? Doesn't look so great. Why? Because of a very, very teeny tiny problem. CP theorem is still there watching you, always watching you, Vazovsky, always. So then one of the nodes is very slow, or one of the nodes is down completely. Desired count of acknowledgements cannot be reached. And that means, well, first we wait, and then we get an exception. Cannot reach desired consistency level. Sorry, come again later. What's just happened? We move it ourselves with consistency level all from AP to CP. So now we are consistent and partition tolerant exactly as you desired, but by the price of availability. Always happy, like that's my favorite slide here, David. Good. Yes, so that's exactly. Helen asks a very good question. What if we have replication factor even and consistency level quorum? It still goes the same way. So majority, so half plus one. Exactly. That's why we recommend not to go with even count of servers, because it's actually economically not reasonable. Best way is to have uneven count of servers, 3, 5 usually recommended values. Yeah. So it will just require more servers to build quorum. So it will be more expensive for you, but will not give you any real benefit. So that's why we go for uneven numbers. So it will work, but it will be more expensive for no reason. At least I cannot imagine anything more reasonable here. Good. Okay. So finally, most of you now must be asking, then if I still want to be fast, and meanwhile I want my data to be like really consistent, what will be the easiest way for me to reach that? Answer is immediate consistency. What is immediate consistency? Concept is purely mathematical. If you write with consistency level plus, sorry, if your consistency level on write plus your consistency level on read higher than replication factor, that means you have immediate consistency. So for example, imagine I have this 6 servers data center and replication factor is 3. And I'm writing with consistency level quorum and I'm reading with consistency level quorum. That's going to be consistency level quorum of 3 is 2. So it's going to be 2 plus 2 equal 4, 4 higher, bigger than 3, and that means I have immediate consistency. It will be the same if I write, for example, with consistency level all and read with 1, 3 plus 1, bigger than 3, or if I write with consistency level 1 and read with consistency level all, 1 plus 3 equals 4, 4 bigger than 3, immediate consistency. But obviously, anytime you see consistency level all, it means you are sacrificing your capability to survive any kind of outage, and that's obviously bad. Now let me explain that. Then
Alex,
yep, sure.
can I jump in on that? What you're sacrificing is your ability to write. But in return, you do get something if you use one and all.
Yeah.
Consistency one, you get very high performance and highly available reads, but
Yes.
lower performance, lower availability writes. So you need to decide what fits your use case.
Yeah, it's use case dependent. So, for example, you really have huge pressure on reads, like really millions of queries per second on reads. This way, you really have to think about consistency level 1 for read and taking care of writes properly. That's a little bit different story, but yes, there are some, like you see, we are speaking about real rocket science. And there are some things to consider. Yeah, like things to consider, for example, to get certified as Apache Cassandra developer, what can totally help you boost your salary, but that's out of scope for today's workshop. So, yes, take a look. You write data on consistency level quorum. That means what you always know what your data was stored on at least 2 servers, otherwise you would get an exception. And then you read data on consistency level quorum. It means what a query coordinator on read will compare two pieces of data or digests of those two pieces of data, see if they are matching, their data is valid, and we return this data to client immediately. If if we imagine this server was not updated, and if we read data from this server as its query coordinator and replica simultaneously, which happens very often, most of the time, and this server responds often faster, but it stores outdated information, not like this one. Then query coordinator notices what data digest is going to be different. And in this case, it will do two things. First, it will obviously get information from this one, a return answer to a client. It will be a little bit slower because of those procedures, but still you get consistent data, which is mostly more important. But also it will initiate repair for this partition, for this server, so it will recover from its inconsistent state and it will never happen again. So when your consistency level write on consistency level read higher together, higher than replication factor, you have immediate consistency and you are good and you are consistent. And that is as close as you can get to the magic middle of this CAP labyrinth. So, what are kind of a consistency levels we have? 1, 2, 3, nothing to explain. We just explicitly specifying how many confirmations we need to have. Then quorum means, well, quorum majority. All means all. There are two more cases to consider. Local one, local quorum, and each quorum. What does that mean? Local is a very simple idea. Local means what I tell to my application to work only and expect confirmations only from the closest data center. Imagine your clients are in the United States and your application runs in the United States. And your data center, you have data center and database instance, data center of a cluster in the United States. You want American customers work with American application and American application work with American data center for the database, not with Australia, not with Europe, not with India, but with America. By saying local quorum, it means I need quorum of the servers from the closest data center, not from the remote one, but from the local data center. This concept must be simple, very simple, so you don't wait for the confirmation of a servers what are being remote to this application instance. So usually for multi-data center deployments, we go with local quorum. And each quorum is the most aggressive consistency level except all. So each quorum says, I need you to reach quorum in each and every data center I have. This way you guarantee what information will be spread immediately all around the world. But obviously, if one of the data centers is down, you're going to wait, and then get an exception because this query consistency level was not reached. Cool. Let's move on. Two questions, and I believe those are last questions from my side. Nope, not last. Okay. And first question is going to be, CP theorem says what on failure? C, A, and P are guaranteed. If C fails, so do A and P. Only CA or CP can be guaranteed. See, people are like answering, but slowly. Yes. That's an intensive workshop. You are learning many new things today. So you will have to think about that then for days. Yes, perfect. Um, CP theorem says what
Yes.
on failure. Only CA or CP can be guaranteed, but or is the key word here. You cannot have all of that. And that's not our fault. Blame Eric Brewer for this discovery. Okay? Good. Okay. Then next question. Tell me, please, recommended consistency level for immediate consistency. Read write 1-1, read write 1-0, read write quorum quorum. Okay, this time it gets faster. We just discussed it, so makes sense. Okay, what's going to be? Yes. So that's a tricky question. Second
Yes.
answer, 1-all is technically correct. With 1-all, you will reach immediate consistency, but it's not recommended. With 1-1, you are not reaching immediate consistency at all. You are just guaranteed to run in a problem sooner or later. So recommended consistency level for immediate consistency is read write quorum quorum. Good. And we are almost done with this part. I don't remember. Okay, well, you know what? I will switch to you, David.
Okay. Very
Hmm.
good. Thank you, Alex. And I
My
do want to
pleasure.
apologize to everybody attending. As you can tell, Alex and I get really excited about this material, and you've been asking great questions. We've been trying to take the time to answer them. So you can see we're kind of pressing our time here, but if you'll hang on with us, we've still got some more hands-on stuff and a little more to do yet.
Yes, exactly.
Next thing we're going to do is create some tables. And in this application, we have sensors of different types on different networks. I believe there's a volcano sensor and an ocean sensor. And here we're having two tables, sensors by network and temperatures by sensor. And notice it says bad. So there's a problem with that one. But let's create them. I'm going to copy the CQL and simply paste it into CQLSH. And it didn't work, so I have to select a key space. So use sensor data, that's the name of my key space. Now I'm going to paste my create statements back in, and the create statements returned appropriately. But if you look at that create statement, this one, this table by sensors bad, this gets to a problem that one of you asked before, and that problem was, what if your partitions are unbalanced? Or what if you have an issue with partition size? What this is going to do is partition based on sensors. So if I have a sensor by Kilauea volcano in Hawaii and another one by a volcano somewhere in Iceland, if one sensor's reading, every 5 seconds and one every 5 days, I will have an imbalance of partition size. The other is, as long as these sensors are running, more and more data is getting read into the Iceland partition or the Kilauea partition, and they're growing unbounded. So you have a problem there in that the partition size will just continue to grow until it exceeds the size available to store on a single node. And one of the guarantees of partitions is that all data in a partition is co-resident, stored on the same node. So that's why this particular data model is bad. It has to do with the partition sizing. So the solution is that we're going to create buckets. Instead of storing all the data, all the sensor data, which may be very high rate acquisition, we're going to store data in buckets by date. So all the data from January 1st will be one partition, all the data, for Kilauea from January 1st, and all the data from Kilauea for January 2nd. So the partition key, which is the inner parentheses of the primary key, will now be made up of two fields. One identifies the sensor as before, the other the date to act as the bucket. So what we're going to do is drop the old table. We haven't put any data in it, so we're just going to drop the table. It take a second or two for that to respond. And then we're going to create the new table grouped by sensor and date. So each partition is a date, or excuse me, a bucket for a specific date. And then we can describe the tables just to see what we've done. And now we have those two tables, sensors by network and temperatures by sensors. And did we create the networks table? I'm not sure, so I'm going to create the networks table just because we'll need it later. And that was a create if not exists, so that succeeded. As I said, I'm following along with the instructions on DataStax Academy or GitHub. You have both links, and you can follow along. I'm going through it kind of quickly, but you can do this on your own afterwards. I'm going to turn it back over to Alex.
Yep, give me a second. A moment. I will let you know when do we switch.
And Daniel, you asked about the certificate. Yes, remember, you will get a badge after completing the course in Academy or GitHub, and there's a quiz at the end, and you'll get a badge after that. As far as the certificates, as I said, we'd recommend that you follow the admin or developer path at DataStax Academy, and that would be two courses, our core fundamentals course and our admin course, or fundamentals in data modeling. And then you can send an email to academy@datastax.com, and you'll see all that in Academy, and you'll receive a voucher to take the certification exams. So coupon for finishing this in the quiz, and voucher for exams after finishing the two Academy courses. And I'll turn it back to Alex.
Yep, already switched the screen, thank you. So yes, we are getting actually to the last part. And thank you for staying with us. You spend your time wisely. So, final part, and that is a very, very introduction into data modeling. Data modeling is a huge thing, and it's extremely important thing. You really need to learn data modeling if you would like to be successful with Cassandra. Actually, it goes to very database, to all the databases when you speak about. That's a fun fact. Last year I was at Mongo conference at Frankfurt, and quite surprisingly, I have to say what their approach to data modeling is nearly exactly the same as ours with Cassandra. It's really so close. Maybe Artem Chibatko will say more about that because I know he did research about this topic. Maybe like you would tell us a couple of your ideas based on that in the chat, if possible. But yeah, the general idea is a very common thing for many of the different NoSQL databases. So let's go. Data modeling is about modeling our data in the right way. And what do we manage? We manage rows, columns, tables, all these kind of things. Yeah, yeah, I would say more than wizard, actually, but yeah, let's go. So a very, very tiny part of it is intersection. It's the intersection of row and column, call it a cell. That shouldn't be a big surprise to you. Then group of cells is a single structure, a data item, and a table called row. Then new thing, group of rows stored together is a partition because they share same partition token. And then finally, table stores partitions, and partitions have rows, and never forget about that. You should never forget about partitions because partitions, they never forget about you. So keep it fair. Good. And data is organized in distributed tables. So, but we discussed that already. Let's move on. Then you create a table. You have to model your data. And very important thing is to choosing, the most important thing might be to choosing the proper partition key, because partition key will decide how data is partitioned, okay? For example, here you see on the temperatures by sensor, we partition our data based on sensor and date. Because they all are becoming partition key, so the temperature was stored at some date, and now we have sensor what stored it. Sensor ID and date will be combined together before making the hash with this murmur-free algorithm based on that. And as a result, all the records for this sensor, for this date, will be stored in a single partition, which will be reasonable for most of the scenarios. If you adjust your sensor, it might become too big over time because every sensor records more and more and more partitions. And if you do something like sensor and timestamp, then you will have each, when you will have as many partitions, as many records you have, which is technically fine. So you can do that. It will work on a write time. But thinking how do you work with Cassandra, working with data in Cassandra, you always have to remember write time, read time, write time, read time. Can I write temperature sensor like that, using sensor and timestamp? Don't forget, on each operation, I need to know partition key, all the parts of a partition key. So when I write it, do I know it? I know sensor ID because it just reported its temperature, and I know timestamp because I know perfectly when it happened. So can I store this data? Yes. But then read time comes, and you are going to read this data. Do you know sensor ID? Let's imagine, yes, your customer just told you, I need to see temperatures for the sensor number XYZ, ID XYZ, so that's good to me. But to retrieve data from the table designed like that, sensor and timestamp, to do it properly, you will have to know all the timestamps of all the records you store it. And imagine you storing your temperature sensor state every second, which happens on factories, for example, all the time. That's not going to be easy to retrieve this kind of data, right? Then, second part of a primary key are the clustering columns. Clustering columns define sorting order, and they define how data physically stored on disk. So, for example, if we store our temperatures by sensor data, partitioning by sensor and date to make smaller partition, and then we use clustering column, timestamp as a clustering column for sorting. So it will be sorted by when this recording was done. It makes totally a lot of sense. So you can order data and retrieve some pieces by date, sort by timestamp. So that makes a lot of sense. That works perfectly. That is a very good example on how to do this kind of things. If you do your primary key with no clustering columns at all, then what happens? As primary key defines uniqueness, you will have in this case only one record per sensor, for example. Uh, if you do record like that, sensor and timestamp as a clustering column, it will work, but all the records of the same sensor will always go to the same partition, and partition will become too big in the end. So you are getting the idea. Now, primary key is something what uniquely identifies a row. It consists of a partition key required and clustering column optional. Now, why I'm talking so much about that? Why data modeling in Cassandra is so deadly? I'm not afraid of this word. Why data modeling is so deadly important? Take a look. Partition keys. Now, attention, please. Partition keys define data distribution over the cluster. Got it? Right? We will get back to that in a moment. And clustering columns define how data is physically written on disk. Now answer a question, maybe not in the YouTube chat, but to yourself. Speaking of the Cassandra typical deployments, dozens to hundreds to thousands of servers, multiple petabytes of data, up to petabytes of data, multiple data centers, constructing a cluster around the whole planet. Can we change partition key? Can we do alter table, set new partition key? What will happen if we do that? that will create new tokens for all the data you have. New tokens, mostly probably, will belong to different token ranges, not where the data was before. So basically, all your petabytes of data in your cluster have to be shuffled, put to another server, because now this server is responsible for this partition. That will take weeks, maybe months to happen. And thus, that is not possible at all. You can, once created, partition key cannot be changed. But the same with a clustering column, as it defines how data is physically written on disk, and we speak about petabytes. Once you change clustering column, it will require data to be rewritten across all the cluster. It will again take weeks and months. So guess what? It's not possible. Once created, data model cannot be changed. You will need new tables and you will need to migrate your data. And if your data model was wrong, then you will have to do a lot of additional work. So stay lazy, do it right from the first. How to do it right? Learn at the Academy. Learn at datastacks.academy. It's a free course on open source Apache Cassandra. Alter table still present. So you can add some fields, for example, so-called data columns. But you cannot do anything with a primary key. That's it. It's immutable. And finally, just three rules to know before we let you go. Rules of a good partition. Store together what you retrieve together. If you are going to read this data together, then obviously you need to store it together so your select query will reach one server, not you will not need to do a dozen of queries trying to gather it all together. Think about partitioning write time, read time, write time, read time. Then avoid big partitions. Designing our partitions based on for our users, our customers, based on the country they live. That's a very bad idea. Some countries are huge. There are so many people. I don't know, like India, China. Well, you know what I mean, like hundreds, millions. But meanwhile, there are tiny countries like San Marino, where maybe I don't know how many people live there, let's say 50,000. That means what some partition will be disastrously huge and some partitions will be tiny. Then your cluster will try to balance, but as balancing is partition based, it will not really work. So you really need to try to create even partitions, so each partition will be more or less similar to all the others. And we very often at this part, exactly as David said, we need bucketing. So we create a partition key not based on just some real value, but also using some synthetic value. Oh, grazie, Christian. Um, but adding some special value in the partition key, so it will be used when creating a partition token, and it will change. So here we add to our sensors also month, year, or date, or week of a year, or just year if you don't have too many records. And then these bucketed value changes. So there is a next month, and again, next month, every time new partition will be created. And that is a very good technique. And then finally, avoid hot partitions. In real life, when we say hot, then that usually we mean something good, right? Something we would like to have. Hot car, I don't know, whatever. But in Cassandra, the hot partition is something you definitely don't want to have. Imagine we have a data center with 100 servers, and we store this temperature by sensor information. And we decide to partition it on date, and we have replication factor 3. If partition is decided on date, that means what all sensors writing data today will write it to 3 servers out of our 100. And those 3 servers will be overloaded because our billion of sensors write to only 3 servers. So workload is not spread over 100 of servers, but only what it all goes to each one of those 3. Then date change, tomorrow comes. Then that's the next partition because it's a new date. New date, great. So again, 3 different servers responsible for all the pressure on them. And now you can say like, we are a rich company, we can afford buying one more 100 servers, and you go do that. Will it help? No, it won't, because it's still the same data center, still the same data model, still the same partitioning, replication factor free, and now three out of your 200 servers will be busy, and others 197 will be idling because they have nothing to do today. They will be busy tomorrow, but not today, right? So this idea on the partitioning by date exactly shows how you destroy perfect Cassandra scalability. And that's what I mean when I say when someone says Cassandra is slow, you just tell him, your data model is wrong. Seriously, man, you should get data modeling course at DataStax Academy. We are working hard, by the way, to revamp it and make it even more user-friendly, although it's pretty good. Cool. Last questions. Question number 8. And all correct answers give maximum points. Select operation, read operation without partition key is a syntax error. It's okay to get all data. It's very bad, or it's illegal and punishable by law. You know, I work in NoSQL police, so if you do select without partition keys, I will come for you. So if you ask me, right answer is the fourth one. It should be illegal and punishable by law. But right answer, select without partition key, is very bad because it leads to full cluster scan. No, it's not okay to get all your data, only if you have 1, 2, 3 servers, and even then it's not okay. It technically does not lead to a syntax error. If you don't specify any verse statement, just expect some stupid results. Yeah. Cool. David, you want to add something?
Yeah, no, I fully agree with this. It is, however, the only way to get all your data. So if you must, but it's still a bad practice. And I agree, Alex should be the NoSQL police.
Yeah. Bad boys, what you gonna do? Okay, next question, and that's going to be your last question, and we will see the leaderboard. We will know who was the fastest, or who was not the fastest, but most correct. 18 players ready, so let's go. Last question, ladies and gentlemen. What is the most important rule of the partitioned data, or most commonly offended rule? Try to have as many partitions as possible. Keep partition size under control. Keep together what you retrieve together. Make partitions bigger. Yeah. Okay. So, yeah, I decided to hide that a little bit. Keep together what you retrieve together is a very important rule of partitioned data. So those gave answer, keep together what you retrieve together, are technically correct, but if you think about that, that's a trap. If you keep together what you retrieve together, that is really cool. And your application will kind of work good for reads, but first it can work totally wrong for totally bad for writes. And second, it still can grow over time the way you cannot fix it anymore. And now you're going to spend months and months trying to decompress your data, split it into multiple tables, and so on and so forth. As long as you keep partition size under control, you might have avoid big partitions. It's hidden rule. Avoid big partitions.
Yeah, and Alex, I'm going to disagree with you a little bit
Yep.
and say that these are both crucially important, and it's maybe a little too subtle of a difference here as to which one is more important.
You see, if my data stored the way so it's not convenient to read, it puts more pressure on me as a developer, right? So I will have to do more work. I will do some maybe application level joins, kinda fake joins, but if I don't keep partition size under control, I might once, our field engineers told me they found a customer with a partition size of 15 terabytes or something like that. And that's not going to work well. And like the whole performance of a database, all of the customers, all of the queries will be affected. So there is a subject to discussion I would like to have with you with some beer in some bar in Iowa, which I hope to reach maybe next year, or might
That
be
sounds good.
you be my guest. I will be totally excited about that. But yeah, we have some beer in Germany. Maybe you've heard
I'm
about
excited
that.
that you do.
Right. But the general idea is, from my point of view and from my experience, keeping partition size under control. But okay, that's debatable. That's something I will agree. So regarding Can I Come, take a look. We are working on the series on the Cassandra Day events over the planet. So subscribe to our channel and subscribe on the Academy. There are some events to be announced. I will be totally happy to have a public discussion and share some beers and like share your experience. And that's totally great always to talk about these things. And Nightbot friendly just pasted our LinkedIn links for today. So that's not just a invitation from politeness, but that's for real. Jump in, use those links, and add us on LinkedIn. We will be totally happy to link with you. Now, and that leads me to the last slide of this thing. I want to see leaderboard. Who was the fastest? So, right answer by Paul, right answer by Mridul. That makes Paul, Tabiso, Budaza, and Watson to share the first place. So Paul, Tabiso, and Watson, that was a truly great job, and congrats for sharing the first place, basically. And Swati, Christian, Mridul, MD. I mean, thank you and everyone participating. There are no prizes today, but you know what? Today you earned a lot of knowledge, and knowledge what makes you better engineer, and better engineers are getting better paid. So in the end, it's a win-win. Cassandra community gets qualified engineers. We desperately need more, and you get better paid. So that's like sounds a very win-win situation to me.
It's
With
awesome.
that, thank you for participating. Last slides. Crude operations will be first step of your homework because we are out of time. So proceed with what David has shown to you. Complete the quiz on Academy. So Data Stacks Academy, you've seen that over there. And what's next? Don't forget to complete your lab. Link with us at LinkedIn. We will be happy. So that was David Chang and Alex Voloshev. Important links you might need. If you have questions, catch us on our Discord server, dts6.io/discord. Learning site and all the courses we have, like big courses and also small workshops, is datastacks.academy. It's under construction, so there might be some uncomfortable points. We're working hard to deliver the best user experience to you, but it comes with some time. Subscribe to new workshops at datastacks.com/workshops, and like and subscribe on this YouTube channel. So stay in touch with us. With that, thank you so much, and we will be happy to answer your questions on Discord.
Thank you, everybody. Thanks for sticking around to the end.
Yep. Thanks, David.
And thank you, Alex.
Yeah, great pleasure to work together, and all of you, so amazing questions. Thank you. It was a real pleasure to work with you today. Thank you for coming.